A story with two different toolkits. Sarah has been a network engineer for 11 years. She is good at her job. She knows the equipment, knows the vendors, knows which alerts are noise and which ones are the beginning of something worse. On a Tuesday night in February, she's sitting in front of 3 monitors with 14 open tickets, 2 active incidents already in triage, and a coffee that went cold an hour ago. At 3:17 a.m., a BGP session drops on a core router at a field office in the Mid-Atlantic region. She sees it, she logs it. She puts it in the queue behind 2 incidents already consuming her attention. At 3:19, 2 minutes later, a temperature sensor in the same rack crosses its threshold. It comes on a different dashboard from a different vendor system with a different alert format. She does not see the connection yet. Nobody would. The two systems were never designed to talk to each other. At 3:21, CRC errors begin climbing on a specific line card in the same rack. Third system, third dashboard, third alert format. 3 signals in 4 minutes from the same physical location in the same piece of infrastructure. And they arrive looking like 3 unrelated problems because the systems that generated them have never shared a common vocabulary. Sarah is experienced enough to know that the correlated failures in the same rack are rarely coincidental. But she is also managing 2 other incidents, and correlation takes time. You have to pull the asset records, check the maintenance history, map the service dependencies, cross-reference the physical location against the logical topology, and do all of that while the alerts keep coming and the queue keeps growing. On a good night with no other incidents running, that is a 20-minute job. Tonight, it is longer. At 3:47, the transceiver fails completely. 2 operational workflows drop. The incident that did not have to happen is now a full outage with a service impact report, a customer notification, a postmortem that will consume most of the following day. Sarah did not make a mistake. She made a reasonable triage decision under impossible conditions with the tools available to her. The tools failed her, not because they were poorly built, but because they were never designed to see what she needed them to see. Now run the same scenario with a different infrastructure underneath it. At 3:17, the BGP sessions drop. The data pipeline has been processing telemetry from all 11 locations continuously, normalizing Cisco logs and Juniper logs and vendor sensor formats into a common structured representation. The feature store has been calculating temperature deviation from a 30-day baseline and the CSC error rate acceleration in real time, all while using the same feature definitions the model trained on. Because training server skew in a network operation context does not produce a slightly degraded recommendation. It produces confident wrong predictions about which equipment is failing and why. At 3:19, the temperature sensor crosses its threshold. The semantic layer already knows that the sensor, this router, and this line card are co-located in the same physical rack. Because the ontology has formally defined what co-location means, and the knowledge graph has encoded those relationships for every asset across all 11 locations. The 3 signals did not arrive as 3 separate alerts from 3 separate systems. They arrived as 3 priorities of one situation. At 3:19 and 400 milliseconds, the model has a hypothesis. The failure pattern matches optical transceiver degradation with a 91% confidence. That confidence score is not a statistical artifact. It is traceable to a specific model version, a specific training data set, a specific validation result, and a specific set of labeled historical incidents that taught the model what this pattern looks like before the transceiver fails completely. The knowledge graph reasons over this hypothesis. Asset 4471 serves 2 active operational workflows. 2 redundant paths exist. Neither is currently carrying traffic that would be disrupted by rerouting. The proposed remediation is compliant with current network policy. The shackle validation layer confirms the assertion satisfies every ontological constraint before it enters the graph. The deterministic policy audit clears the action. The reasoning chain is complete. At 3:20, Sarah's screen shows a single out notification, not 14 alerts from 4 systems. Not one notification with a specific hypothesis, a confidence score, a list of affected systems, a proposed remediation path, policy clearance status, and a full reasoning chain that she can read in the time it takes to pick up her coffee. She reads it, the reasoning holds, she approves. The transceiver is isolated at 3:20 and 30 seconds. The operational workflow never dropped. No service impact report. No customer notification. No postmortem. Nobody files an incident report because there was no incident. Sarah did not become less skilled between the first scenario and the second. The infrastructure became worthy of her skills. Every layer that the machine learning stack this series has covered contributed something to that 400 milliseconds. Remove any one of them and the story ends the way it ended the first time. This is what the autonomous NOC looks like when every layer has to work.